What's up guys, my name is Ehsan. Welcome to my first tutorial on BFS. In this introductory tutorial, we are going to see some basic graph terminologies, graph representation, and then BFS algorithm. And then in the second tutorial, we will be implementing BFS in C++. If you are well acquainted with graph and BFS, then you can skip this video and watch the second tutorial. So let's get started. Before moving to graph representation and all those cool stuff, let's first of all see what exactly the difference between a tree and a graph. In trees, there is a hierarchical relationship between parents and children. That is, one parent and many children kind of relationship. And in graph, relationship can be from many parents to many children. Unlike trees, graphs may contain cycles. Basically, graph is a non-linear data structure, just like trees, which is made up of vertices and edges that connects them. By non-linear, I mean they require a 2D representation, unlike linear data structures like arrays, stacks, and linked lists. Now let's look at a more common definition of graph. A vertex in a graph is basically a discrete position in the graph, and an edge is a link between two vertices that can be either directed or undirected, and the edge may contain some cost associated with it. Undirected edge from A to B means you could move from A to B or from B to A, but a directed edge only allows travel in one direction. This graph is an undirected graph, and the directed graph looks like this. There are basically two standard ways to represent a graph. One is using adjacency list and other is using adjacency matrix. First of all, we will see what is adjacency matrix. It is a 2D array of size v cross v, where v is the number of vertices in a graph. Here 1 indicates that there is an edge from vertex 1 to 0. You can see in the graph. If your graph contains weight, then you can put the value of the weight instead of 1 here. The cool thing about adjacency matrix is removing an edge takes just a constant time. Queries like whether there is an edge from vertex u to vertex v can also be answered in constant time, order of 1. And these metrics are always symmetric, but the disadvantage is very huge because it consumes more space. You have to allocate a 2D matrix, 2D array of v cross v. Suppose the size of the vertices are increased from say 1000 to 1 lakh. Then you can't create a 2D array of 1 lakh cross 1 lakh because of memory limit. To overcome the disadvantages of adjacency matrix, adjacency lists are used, and they can be implemented quite easily using linked list in C. Now let's move on to our BFS. BFS is one of the simplest algorithms for searching a graph. Dijkstra's single source shortest path algorithm and Prim's minimum spanning tree algorithm uses similar idea like BFS. Basically, traversing a graph means visiting all the vertices in the graph exactly once. So we do not want to visit the same vertex twice. We can easily achieve this by marking the vertex as visited once we have explored it. Actually, what BFS exactly does is it explores the edges of graph to discover every vertex that is reachable from the source. And now this is our algorithm which we will be implementing in our next tutorial in C++. Here I have used a queue data structure. If you don't know what queue is and what it does, then look at this. Queue is the first out kind of data structure. It means that the first thing you add to the queue will be the first thing you get when you perform a pop operation. Now let's run our algorithm in one example. For the sake of simplicity, I have used an undirected graph and I have assumed that all the vertices are connected. Here you can see that we are given a starting vertex from where we have to perform our BFS traversal. The first thing which we have to do is mark the starting vertex as visited and then push that vertex in queue. Now while queue is not empty, what you do is pop the front element from the queue and enter the inner for loop. Here pop S. Actually what this orange color means this vertex is visited and is currently present in queue, and this purple color means this has been popped out from the queue and explored, and this sky blue color means neither visited nor explored. So after entering the inner for loop, see all the neighbors of popped element X and push them in queue if they are not already present in it. Here see the neighbors of S are R and W. Push them in the queue and mark S as explored and R and W as visited. Now keep on doing all these steps until your queue becomes empty. So after this, pop out W and mark it as explored and push all its neighbor in the queue. Then just, I think all these are pretty much self-explanatory. Do the same steps. Once your queue is empty, it means that all the vertices are explored successfully, or you can say all the vertices are discovered. Now let's look at the running time complexity of BFS. The operation of enqueuing and dequeuing, or you can say pushing and popping in the queue, takes a constant time. So the time complexity of BFS is order of E plus E, which is linear. That's all for this tutorial. Thanks for watching this, guys.